Hi everyone, welcome to our MTP presentation. We are the design and implementation of a robotic mobile-based MTP. I'm Kenneth Alejo.
I'm Alex Corey.
I'm Braden Foley. I'm Andrew Jackson. I'm Tim McCarthy.
And our goal was to design a modular mobile base for robotic arms. So a little bit of background really quick. There's hundreds of different robotic arms that are used worldwide for a variety of tasks. Some tasks include research, service, and industrial and manufacturing robots. One thing that most of these arms have in common is that they're typically bolted to a rigid base that's not electric. So our project was trying to find a way to make it so that these robot arms can be mounted on a mobile base and expand their functions.
In order to achieve this goal, we had to come up with some objectives. So, of course, our first with a mobile base is making it mobile. So mobility was important. We wanted it to be able to move around and enhance its workspace. At the same time, we wanted it to be able to fit through doors to be economical and also reach countertops and maybe even tall cabinets. The second aspect or objective was modularity. So we wanted the arms to be hot swappable. That means with one click, it would be able to operate as any other arm would be able to in our robotic base. At the same time, we also wanted reliability. This is going to be working around with humans in industrial purposes or research, so we wanted to be safe. And we wanted a robust design so that any arm that was implemented in the base would repeat the same exact task. So in order to come up with an initial design, we did some background research. As you can see on the picture on the right, that is what we call the generic one and done base, where there is one specific robotic arm that fixes to a specific mobile base. This arm can only attach to this mobile base, and vice versa. This base can only attach to this robotic arm. But it's still important in what we use for the basis of our mobile robotic base. On the left, you can see a CNC mill carousel. We use the kind of modular design concept of that. It can house any tool, no matter shape, size, or functionality, and we want to use that design concept when implementing our arms in our mobile base. This is an exploded view of our proposed design, where we will be talking about mobility and modularity, as well as reliability in our design. We'll be starting with a breakdown of the chassis and drivetrain with.
Thanks, Braden. So the satisfying part of our mobility objective, we wanted to create a robot that would be able to be extremely maneuverable. So we opted to create an autonomic drive-based system through 10 wheels in tandem with a spring-based suspension, as seen by this little image. To the left, you see what this autonomic drive is taking. Each red arrow represents a possible direction that our robot would be able to travel. As you can see, it's extremely versatile, which is exactly what we're looking for. We also wanted our robot to be able to fit through a standard door of 30 inches. And as you can see here, our robot comes at a width of just 28 inches, giving us 2 inches of clearance and allows us to have a very large workspace area. So we can now travel through different rooms. The second element of our project for mobility is an elevation system. We utilize 3 independently actuated cinder jacks, such that we can now have an additional 24 inches of vertical workspace. Because the jacks are individually actuated, this allows us to fit, as seen by this picture. This allows us to reach higher highs and lower lows. This is all in thanks to our elevator alignment system as seen on the bottom. Now Alex is going to talk to you about modularity.
Thank you. So on the modularity front, we start off with on the right there, the universal plug. What that does is allows us to feed through power and data from our base to any arm we can. And if we're able to mount any of these arms to this, the black insert down here, this allows us to take whatever arm, whatever controller, they all have their own, and just mount it directly to it, and all data power just gets fed through. These then can mount on our home base, which also acts as a charging station, to allow for any range of these to be set up and have the robot go as it needs to go throughout the different rooms. Further down in the modularity aspects, we have a configurable arm detection, which allows us to set what arm is attached to these inserts to allow the base to automatically know what arm it's talking to. This allows for a control abstraction to allow the base to just get any commands that it needs to say, hey, arm, go to this position, and no matter what arm's on there, it'll know what to do and be able to go right for it.
All right, and finally we have our reliability and safety goals. So first, you can see the battery management system. This battery management system provides overcurrent, undercharge, and overcharge protection to make sure that the batteries are in a good state of health. It can also monitor how much charge is on the battery and tell the robot base to go back to its charging station in order to charge itself. In the middle, we have the limit split table calibration. These switches are used so that when the jacks depress, it'll go and hit the limit switches, thereby zeroing the position of the jacks. And in addition, it will also be a soft stop that keeps the jacks from depressing too far. Finally, before implementing our code on our actual physical base, we made sure to create gazebo simulations of our robotic base so that we could test the theory of our code before putting it into practice.
And so here's a couple pictures of our robot. On the left, you can see we're using the Innova Gen 3, and on the right two pictures, we're using the Franca and the Panda. You can see in the right two pictures that we are demonstrating our full range of motion here. So we're coming really low to the ground in the middle picture, reaching up to high cabinets on the right picture. And we also have some videos. So on the left, you can see us manually hot swapping the arm insert. So you can see we press a button, lift the insert right out, and put it in the home base for storage. In the middle, you can see that we have full tiltability, so we can reach even lower. And then on the right, you can see the robot slowly rising up into the modular insert, where it just automatically snaps right in, and then it can pull out, and then it just has an arm to do its whatever tasks it does. We also have one final video. The robot doing a full task. You can see it's at 5x speed, so we can drive up to anywhere we want. We're going to raise the elevator jacks. We can use a robotic arm to perform a task, in this case grabbing a water bottle. And then the arm comes back to its home position, the elevators come down, and the base can just drive off and go perform another task. So just to wrap up, we have a couple recommendations for anyone who would like to work on this project in the future. Number one would be an improved autonomous mode. So that would mean adding more sensors, like a camera or an inertial measurement unit, and then combine all of them using sensor fusion to create a more robust simultaneous localization and mapping model to know where the robot is in a room. And then we also would like to see a reevaluated drive mechanism. So that would mean switching to maybe direct drive or swerve drive to better fit our size parameters, and then also provide better performance in terms of speed and maneuverability. And with that, we'd just like to thank Professor Michelson and Callie for all their help throughout this whole project. And huge thanks to our sponsors as well. And that will do it for our presentation. Any questions?